See, the next process other than adiabatic process, what we need to learn is polytropic process. Okay. Polytropic process is a process which is assumed to be reversible, because we can only say a polytropic process exists when there is a process curve present, which means there is a relation between the parameters which is present, pressure volume relation or temperature volume relation, something like that. If it exists, then only we say there is a polytropic process. And let us do it first for an ideal gas. Generally, just like how we get the process PV raised to power of gamma is equal to constant for a reversible adiabatic process, likewise, if it is a polytropic process, then we should get a similar relation like this. PV raised to power of x is equal to constant, TV raised to power of x minus 1 is equal to constant, and t raised to power of x and p raised to power of 1 minus x is equal to constant. Okay. If these three equations are valid for some value of x, that is a generalization here. Okay. For some value of x, if this is found to be or this relation is observed, then we say it is a polytropic process. As per thermodynamics first law, delta U is equal to Q plus W. Q is equal to N Cm into delta T, and Cm is equal to Q by N delta T. This is what we know. Okay. And we do not know what kind of a process this is. That's why we are writing this is a general heat. This is a general heat, specific heat, molar heat conductance, and that is equal to Q by N into delta T. Delta U is equal to NCV delta T. For an ideal gas, that is always true. Work done is equal to minus P into dV, and since it is reversible, P external will be equal to P. Okay. So, for example, if there is any small change in the internal energy, and work done is given as minus P into dV, dq is given as NCm into dt. If these are the terms which we have given, then what we can say, du is equal to, dq plus dw, correct? So du is equal to dq plus dw. So simply showing this value, NCV delta T, NCm delta T minus P delta V. This is what is the thermodynamics first law. Now, consider if this is valid, TV raised to power of x minus 1 is valid, and that is equal to K for a polytropic process. If at all I differentiate this on both sides, so what do I get? This is a differential of UV, right? Differential of two parameters, that makes it V raised to power of x minus 1 into dt by dt will be 1, and then t into this is x minus 1 v raised to power of x minus 2 into dv by dt is equal to 0, right? So I'm differentiating this entire left hand side and right hand side with respect to t. So on doing that, now you can see v raised to power of x minus 1 comes out to be common, so you can delete that. So what is left is v raised to power of x minus 1 by v, so that v will remain here. So 1 plus t raised to power of x minus 1 by v into dv by dt equal to 0. And if I multiply everything with dt, so dt plus t into x minus 1 by v into dv equal to 0. So now dv can be replaced in terms of dt. Okay. So dv part can be replaced in terms of dt as minus v by t into x minus 1. Okay. And that's what I'm trying to do here, because I want everything to be in terms of dt. So this dv I have replaced with this one as minus v into minus v by t into x minus 1. Okay. So this minus will minus and this minus will make it as plus sign here. Okay. And now, as per ideal gas law, PV is equal to nRT. So PV by T can also be written as nR. And you can see this is PV by T. So that PV by T can be written as nR. So now what we got here is dt, dt, dt being same, I can cancel it off. Okay, and n and n can be cancelled off. What is left is simply Cm is equal to Cv. If I take it to the left hand side, it will become minus R by x minus 1. Or this minus can be converted into plus sign here, making this as 1 minus x. So this is Cv plus R by 1 minus x. So Cm is equal to Cv plus R by 1 minus x, and this becomes the uh, specific heat for a polytropic process. Okay, molar specific heat for a polytropic process. This x is any general x now. So for a different value of x, we should get different processes. For example, if I put x is equal to 0, okay, you know that in PV raised to power of x equal to 0, if x is equal to 0, what does that supposed to mean? It means pressure should be constant, right? If pressure is constant, that means it must be isobaric process. So when x is equal to 0, it will become an isobaric process, correct? And the Cm will become Cp, and Cp is equal to Cv plus R. And this we have already proven earlier, isn't it? So that suggests that it is a polytropic process. I mean, polytropic process is a generalized process for different values of x. Okay. So for one value, we are able to prove it correctly that for x is equal to 0, we get isobaric process. If we put x is equal to 1, then it will be 1 minus 1. If it is x is equal to 1, PV raised to power of 1 is equal to constant. This is observed when it is isothermal process, isn't it? So if it is isothermal process, temperature is not changing. If temperature does not change, can we define what is, molar heat capacity? No, right? Because it has to be N by delta T. If there is no change in delta T, no change in temperature, delta T should be 0. So Cm is not defined. And that's what you will notice here also. Cm is equal to Cp plus some value which is not defined. So which means the overall value is not defined here. So since it is not defined, it has to be an isothermal process. Got it? And next, if x is equal to infinity, see, if you write it this way, PV raised to power of x, see, PV raised to power of x is equal to constant. And I multiply both sides with 1 by x. Okay. So then this will become P raised to power of 1 by x into V raised to power of 1 equal to K raised to power of 1 by x. Now put x is equal to infinity. If x is equal to infinity, this will become 0 and this will become 0. So P raised to power of 0 is 1, K raised to power of 0 is 1. So what are we getting? V is equal to 1, which means it is constant. Isn't it? Volume is constant. So when x is equal to 0, x is equal to infinity, you will get volume being constant, and we learned this process that is called isochoric process. Okay. And V is equal, Cm will become equal to Cv because this factor will not be there anymore. Okay. That will be 0. And lastly, if you have x is equal to gamma, PV raised to power of gamma is equal to K, then that is called as adiabatic process. And what will be the value of Cm here in that case? Cm will be equal to Cp plus R by 1 minus gamma. So this is the value of Cm, right, for adiabatic process. Everybody clear on this point? Okay. So basically, we are trying to figure out some kind of a generalized process, and it should be reversible generalized process where we can have these kind of equations valid. That is PV raised to power of x, TV raised to power of x minus 1, and this one. Okay. I suppose this part is clear, everybody. Okay. Now, if you ask me what kind of questions that can be asked here, right? So from the polytropic process, how it can be asked here. Let me give you one question before we go further. Okay. Suppose if I give you that uh, PV raised to power of 2 equal to constant is a polytropic process. Say polytropic process. Okay. If this is the graph, clear? Now if for this process, how does it impact an expansion? Okay, if the expansion happens, if the expansion takes place, okay, find value of work done, delta u and q, for an ideal gas, system. So if this is the case, right, what all factors we know now here? We are trying to expand the gas here. So check out, if x is equal to 2, that is the condition here. If x is equal to 2, I can calculate Cm. Cm will be equal to Cv plus R by 1 minus x. So which is equal to Cv plus, sorry, I forgot to mention that this is monoatomic ideal gas system. So Cv plus R by 1 minus 2. So that will make it Cv minus R. So here I got a process where the heat capacity is Cv minus R. And you know that for monoatomic gases, for monoatomic gas, Cv will be equal to 3 by 2 R. So in that case, Cm will be equal to Cv minus R, or this is 3 by 2 R minus R. Got it? So that makes it R by 2. So heat capacity value in this case is R by 2. And what happens to the work done now? Work done, W will be equal to minus integral P external into dV V1 to V2. This is how we write it. Now what about the pressure here? So I can write it as simply P of gas into dV V1 to V2. And pressure of gas can be written in terms of this value here. So that will be equal to some constant by V square integral V1 to V2 into dV. Okay, with a minus sign. So that will be equal to minus of, okay. So if I take this k outside, so what would I get here? This will be v raised to power of minus 2 plus 1 by minus 1 into v1 to v2. So that minus minus will get compensated. So we'll get this as k into 1 by v2 minus 1 by v1. This is what you will get. Clear? So if these values are being given to us, then it will be easier to calculate the work done. But this is how typically you get the work done formula as well. Okay. Delta U will still be the same, which is equal to NCV delta T. Okay. NCV delta T. So N into 3 by 2 R into delta T. So delta T can also be predicted based on whether V1 and V2 values are given. If those values are given, you can calculate delta U. And you can also say what is the Q value. Q value will be simply, we can write it as N Cm into delta T. And Cm value, we already got this. So N into Cm value, we got it as R by 2. So R by 2 into delta T. So depending upon what all factors that is being given to you in the question, you can calculate accordingly. Clear? Suppose if the question is asked about, we need to comment. Let's say I am supposed to comment on the fact that whether there will be any, suppose if there is an expansion here, okay, expansion here, then what happens, as you increase the, as you are increasing the volume, what happens to the temperature? So we need to comment on temperature factor, let's say, okay, due to expansion, volume increases, which means V2 has to be greater than V1. And we know that TV raised to power of TV raised to power of x minus 1 equal to constant for a polytropic process. Now, since x is equal to 2, so I can say TV raised to power of 1 is equal to constant. Now notice that T is actually inversely proportional to volume, isn't it? It is inversely proportional to volume. So if volume increases, what happened to the temperature here? Okay, it should decrease, right? TV raised to power of x minus 1 this is. So this is x, we got it as 2 here. So it shows that as the volume increases, as volume increases, what happens to the T? It should decrease. So therefore, on expansion, on expansion, what effect you will see? You will see cooling effect in the system. You will notice that it will come to be cooling effect in the system. Everybody, is this part clear? Any doubt here? Right. Okay. So now let us try few questions. Okay, I'll start listing out. Correct. Uh, various questions here. So first we'll start with basic ones because I've already written some questions which are something which we need to learn the graph and everything. Okay, but for before that only I want you to go through some basic questions. So let's see whether you are able to get this, and then we can go discussing the rest of the questions. So please start solving. I'll add one of the questions here. Check. Okay, I need to you're supposed to calculate q w delta u delta h, okay, for isothermal isothermal expansion, if ideal gas ideal gas goes from 1 atm to 0.1 atm at 300 kelvins, if 300 kelvins for 1 mole of for 1
Sir,
mole. हाँ बेटा.
your screen is frozen at a point.
Sorry, can you see it now?
Yes, now it is.
Right, see, this is what you're supposed to do. Calculate QW delta U delta H for isothermal expansion if ideal gas goes from 1 atm to 0.1 atm at 300 kelvins for 1 mole of a gas, and we are taking two conditions. First, if it is reversibly operated, and second case if it is irreversibly operated. Okay, always try to emphasize what is given in the what is the process given. That is the first thing you should notice. What kind of a process is this one? So it's clearly mentioned it is an isothermal process. So since it is an isothermal process, you try to relate this. Delta T will be equal to 0. And you know that delta U for an ideal gas is NCV delta T, which will also be 0. Delta H, which is equal to NCP delta T, that will also be 0. So first we found out two parameters, delta U and delta H, both are actually 0. And since delta U is equal to Q plus W as per first law of thermodynamics, So that implies Q now will be equal to minus W. And minus W reversible isothermal, we have already derived a formula, that is minus 2.303 nRT log of V2 by V1. And since the volume terms are not given, but this time we have been given a number of, what do you say, pressure terms. So the same formula can also be written as nRT ln P2 by P1 by P2. P1 by P2. Sorry, this is not log. So log of P1 by P2. So check out, work done reversible isothermal is equal to minus 2.303 into 1 into 8.314. If at all I have to express that in terms of joules. Okay. So if at all I'm expressing that in terms of joules, that into temperature, which is 300 kelvins given, into log of, you know, uh, P1 by P2. So P1 by P2 is how much? P1 given is 1 divided by P2 given is 0.1. So that will be log 10. So log 10 is 1. So minus 2.303 into 8.314 into 300 joules. Done. This is what you will get. Okay. Let me give the exact value as well. So meanwhile, please check whether you are able to get that. So what we are getting is 5744.14 joules or 5.74 kilojoules. What if I want to write it in calories or kilocalories? See, the same value, if at all I write in kilocalories, you just have to divide it by 4.18. So that will become kilocalories per kilocalories. Okay. So this, if at all I divide it by 4.18, so approximately, or 4.2, you can take directly 4.2. You will get this as approximately minus 1.374 kilocalories. Reversibly, how to operate, is this clear, everyone? This is about the work done. What about the heat here now? The heat in this case will be equal to Q, which is equal to minus W. So Q of system will be equal to minus W of system. In this case, work done by the system is minus of 5.74 kilojoules. So therefore, Q of the system will be equal to 5.74 kilojoules. This is operating reversibly. Okay. Let's see if you are doing irreversibly. If at all, we are trying to do the same thing irreversibly. Second part, for irreversible process, the delta U is still going to be zero only, because this is still an isothermal process. So these things will not change. Q will still be equal to minus W, but work done irreversible isothermal will be simply equal to integral P external into dV V1 to V1 to V2. This is a general formula. And we know that if it is irreversible, it will always happen at a constant pressure. So pressure term can be pulled out of that, and you will get, this is the formula. So therefore, W is equal to minus P external into V2 minus V1. Now, this is the formula that we need to use. Got it? Now, here is the interesting fact. There is no volume term that is directly given to us, and neither the P external is given. But you should realize that in a process, if it is an irreversible process, the reaction will only stop when the final pressure will be equal to external pressure. So external pressure will always be equal to final pressure of the gas. Okay, which we'll write it as P2, let's say. So therefore, this will be equal to minus P2 into volume can be written as nRT divided by P2 minus nRT divided by P1. So nRT is the term which will come common. So nRT can be pulled outside. And now P2 can go inside. So it will become 1 minus P2 by P1. Correct. So this is the work done formula that you need to use. So minus 1 into 8.314 into 300 into 1 minus P2. P2 was given as 0.1 divided by 1. Right. So you can notice that pressure given is point 0.1 going towards 1 to 0.1. So that makes it minus 8.314 into 300 into 1 minus zero point 0.9. So zero point 0.1 which is 0.9. So therefore 8.314 into 300 into 0.9. So that makes it minus 2244 joules. So minus 2.244 kilojoules. Okay. And this is what we expect also, right? Because work done in reversible expansion should magnitude wise should always be greater than irreversible. So that is what we can see from this both equations. So magnitude of reversible isothermal expansion is coming out to be greater than irreversible isothermal expansion. Okay, this is the conclusion also we can draw. Everyone, please check this out. ये बताओ. Right. Let's see the next question. This time, what I'm trying to do, if you take an ideal gas at for an isothermal expansion, but it is happening in two steps. Okay, so it's happening in two steps. So let me write down that question. So for 1 mole of an ideal gas, 1 mole of an ideal gas, okay, is subject to isothermal expansion in two steps. It is going from 10 atm 10 atm 10 liters to 100 1 atm 1 atm and 100 liters. Okay, so during the expansion during the expansion, P external is equal to 5. P external is equal to 5. for first step and P external is equal to 1 atm for second step. Okay, for second step. Calculate Q net and W net. What is the net work done and what is the net Q value? What is the heat? See, throughout the process, you would notice that there is no change in the nature of the process, which means it is remaining isothermal. So delta T equal to 0 throughout the process, whether it is step 1 or step 2. So delta U1 plus delta U2, both the steps would remain 0, as delta U1 is also 0, delta U2 is also 0. That is between step 1 and step 2. Same way delta H1 plus delta H2, that is also 0, implying that delta H1 is 0 and delta H2 is also 0, because it is remaining isothermal all the way. So Q step 1 must be equal to minus W1, Q2 must be equal to minus W2, and Q net has to be equal to Q1 plus Q2, and W net has to be equal to W1 plus W2. Okay, and of course Q net will be equal to minus W net. These are the terms which you know. So what about the work done in step 1? In step 1, it has to be minus P external 1 into V2 minus V1. Has the question anywhere mentioned that it is irreversible? Or is it mentioned it is reversible? No, right? But based on the data, you need to realize, because questions not provide you this data, whether it is reversible or irreversible all the time. Now notice this one. Initially, a gas is present at 10 atm and 10 liters. This is pressure and volume condition. Correct. Now, if you maintain the external pressure as 5 atm and the gas pressure is at 10 atm, so naturally there will be an expansion. So, if it is a spontaneous expansion, will it be reversible or irreversible? It has to be always irreversible. Correct. So, there is a drastic difference in the pressure. So, sudden change will happen. So, without even giving that information, whether it is reversible or irreversible, you should realize that it is in fact irreversible. So, since it is irreversible, now what would happen to the this one? Minus 5 into V2. V2 is how much? And if you notice that V2 is not given, that when P external is 5, where will it actually stop? Because it is happening in two steps, means first it will stop and then it will go further, right? So let me put it in a graphical way to understand this again. So from here, I can say, if this is pressure versus volume graph, so from here to here, it is going, you know, uh, like this, right? No, I curve is, yeah. Now, see, so I can say, yes, there is a, curve which is going like this, right? So in this case, imagine if the pressure here is P1, V1, correct? So from this point onwards, from here, it has reached to a new point. It has reached to a new point somewhere here, let's say. This is that new point where it has reached. Okay. And from there, finally, it has reached to this point. And here it is P2 and V2. Clear? Now, this is like that pit stop. This is step 1. And after that, this is step 2. Clear? But is it reversible? Since it is not reversible, I can remove this process curve, everybody. Isn't it? Since it is irreversible, there is no process curve that will be present like that. Okay. And now, since the P external should be always equal to the final pressure, here, let's say this I'll call it as P3 and V3. And you know that P3 is equal to P external 1, P external 1, and which is given as 5 atm. And you know that as long as we have the same gas maintained at a constant temperature, Boyle's law is valid because everything we are working out is in a closed system. So number of moles are not changing. So I can say P1 V1 will be always equal to P3 V3 will be always equal to P2 V2 because Boyle's law has to be followed all the time. So from here I can say V3 has to be equal to P1 V1 by P3. P1 V1 is given already. P1 V1 given is 10 into 10. And P3, how much is the pressure as it reaches to the uh, a point here somewhere, like a step 1. So that is given as 5. So which means it is 20 liters, isn't it? So we started off with 10 liters. Now it is expanded up to 20 liters. So this one is supposed to be V3 minus 1 then. So this is V3 minus 1. And now V3 is given as 20 liters. Minus initially it is 10 liters. So this is minus 50 atm liter. This is the units. This is the amount of work done. Everybody clear on that? Acha, graphically, how do we measure this work done? See, if you notice that carefully, this is the area we are looking at. This is the area. Yes or no, everyone? So this area will be exactly 50 atm liter units. Okay. And now if you notice the second one, now from here it is going all the way to this point, which is 1 atm. Correct. So after this, what is the work done you are exactly trying to figure out from here? Now this time the work done, what you're trying to figure out is this one. This is the area, which is the work done in the second step. This is the work done in the second step. Okay, so let's see. Let us calculate W2. So W2 will be equal to minus P external into V2 minus V3. So from here, minus final pressure is 1 atm. That into V2. Finally, we are reaching to 100 liters. Correct. Yeah, that's what the question says. It is reaching to 100 liters. Minus we got earlier as 20. We got earlier as 20 liters. So that is minus 80 atm liter. So this area would be around minus 80 atm liter, and this area would be around minus 50 atm liter. Yes, everybody. Okay. Now, imagine if it was only in one step. Okay, so total, let me write down first the total work done. Total work done or W net will be equal to minus 130 atm liter. This is 130 atm liter. And that makes it total net work will be equal to minus W net, which is equal to 130 atm liter. Okay. Now you should realize one thing. Okay. 1 atm liter is approximately equal to 101.3 in joule units. So whenever you have to convert that, you just need to multiply with this number. So 130 into 101.3, this will turn out to be in joules. Okay. So if I want this in kilojoules, so then it is 130 into 0.1013. correct? So that will be in kilojoules. Everybody understood what is Q net and W net? Please go through it. If you have any doubt, you can ask me. Finished? Okay. Now in this question, like I said, what if we go with one step? Okay. Okay. What if with one step, suppose for one step process, then work done W net, net work done will be equal to simply area under this graph, right? From here till here, this is the area under the graph. This is the area we need to look out for. So pressure value is 1 and volume is changing from 10 to 100, correct? So therefore it is going to be minus 1 into 100 minus 10. So this is minus 90. Okay. So it is supposed to be minus 90. Correct. So minus 90 ATM liters. But if you do it in same amount of volume change, but you're doing it in two steps, how much is the work that needed to be done? Minus 130. What is the learning from here? Which means if you are operating something irreversibly, in one step the work done for an expansion, one step the work done required is less. But if you do it in two steps, it will be slightly more. If you do it in three steps, even more. Four steps, even more. If you make infinite steps, that means it becomes reversible. That is a maximum work done. So now, lot of time questions will be asked in disguise. That is, calculate the maximum work done that you can get out of a system. So when I say maximum, that means it is reversible. So for an expansion, maximum work done is always reversible work done. For a compression, maximum work is always irreversible work done. So remember the question what is being asked, okay? Whether it is compression asked or whether it is expansion asked. If it is compression, you should calculate what is most irreversible work done. If it is reversible, that means if it is expansion, you are supposed to calculate a reversible work done. Okay, clear everyone? Right. Let's see. Before going into the further question, let me just give you some briefing on graphical representations. Got it? So before we go further, let me give you some graphical representation or what we call it as graph transformation. Suppose if I draw P versus V graph, P versus V graph, okay. First, I'm doing everything for isothermal process. Everything I'm doing is for isothermal process. In that case, P versus V graph will be like this, correct? Now, suppose if at all I say there are multiple number of steps that are happening and it is a cyclic step. So suppose from here, if at all I give it, sorry, P versus V graph is like this. Then what about the T versus P graph or T versus V graph? You know that since it is at constant temperature, this is how it will go. Constant temperature, even the volume changes, this is how it goes. Suppose if it is an expansion, this is the arrow you will use. And since it is expansion, the pressure is decreasing. So in this case, the arrow you will use it like this. This is what I meant expansion. And here, if expansion is happening, volume has to increase. This is the arrow you use. Okay. All of these represent isothermal expansion. Isothermal reversible expansion. Those are the graphs. Clear? Likewise, we can have isobaric. Likewise, we can have isochoric. What if we have combined graphs? Suppose if a graph is like this, where we have pressure and volume graph is given, but now it is given as a cyclic process. And this is how the cyclic process has been given. One second. Let me resume the working now. Check. For a cyclic process, let's say this has started from a position A, B, C, D. Okay. Usually, in a cyclic process, we write this as a cycle A, B, C, D, A. This is what we meant that cycle is completed. This is how the representation will be. Now, go to the if you go to the process one by one, you will realize that the first process A to B is isobaric, isobaric, and that is also expansion happening, correct? Second case is B to C. B to C is isochoric, isn't it? This is isochoric. And third case is what it is? Isobaric. Again, it is expansion. Fourth case is isochoric. In isochoric, since it is at constant volume, we cannot say it is expansion or compression. Okay, clear, beta? Now, suppose if I want to transform this graph in the representation of temperature and volume or pressure or temperature like that. So in that case, how does the graph look like? Let me take this one and explain again. Suppose for this same cycle here. So first graph we are transforming is to temperature versus, let's say, volume. Okay. So first one is isobaric process, correct? So if it is an isobaric process, it is operating at constant pressure. So tell me, at constant pressure, what should happen to the graph usually? At constant pressure, one thing we know that at temperature will be directly proportional to the volume, isn't it? So if volume increases, temperature will also increase at constant volume, at constant pressure, sorry. Charles law. You're supposed to apply Charles law here, A to B. Now tell me, for A to B here, this is an expansion that I need to show, isn't it? So which means I need to show some kind of a line, right, which is passing through this way. Once again, It might be a line which is passing like this, isn't it? Clear? Now, whether it is this line or whether it is a line like this, that is something which we will be able to learn it in a minute. Okay. So imagine this is the first line, A to B. Either it could be this way or it could be this way. Hmm? But it should pass through the origin. That is important part. As it is operating at constant pressure. Second, B to C is a pressure increasing now. Pressure is increasing, isn't it? But operating at constant volume. Now tell me, at constant volume, if pressure increases, what should happen to the temperature? Temperature should also increase. So that means I should go at a constant volume, I should start increasing the volume. So that means A to B line has to be at the bottom first so that it can go up and touch somewhere, right? So that means now this time from here to here, somewhere there must be a line here like this. This is the line we are looking out for, correct? And thereafter, this must be something like B to C. This has to be B to C. If this is A to B, then this has to be B to C. Okay? Sorry, this has to be B to C. So one thing we learned that the point here is actually B. The point here is actually C. Clear, everybody? Now again from C to D, we are making a isothermal. Sorry, this is compression. Okay, earlier what I wrote that was wrong. It was compression. So we are seeing a compression happening. So definitely volume should decrease. So this is how the direction it should go. So definitely it will go here. And again, there is an isobaric process, isochoric process, which means this is how it should go, right? So one more line I will search for should be like this. Okay, somewhere here this way on that graph. So in total, now if you notice from where to where we have marked out, you will see that this has to be your A, this has to be B, this has to be C, and this has to be D. So that means A to B, B to C, C to D, and D to A. So this graph is same as this ABCD graph is exactly same as this graph, ABCD graph. Everyone clear on this term? And if you do the same thing for, let's say, temperature versus pressure now. If I do the same thing for temperature versus pressure, how does the graph transformation look like? Again, at B to C point is a constant volume and D to A is also a constant volume. You know that for a constant volume part, you will again notice the same thing that it should pass through the origin like this. Okay. So first write these two lines and then let us write two more lines which are pressure based, correct? So pressure based lines, constant pressure based lines will be one line here. Let's say one line I have written it here like this. Okay. Now starting with the first point, what is happening from A to B, your isobaric process. So somewhere from, let's say, from A is here, right? A to B, if it is at constant pressure, it is going here, let's say. Okay. Thereafter, B to C, it should remain constant, but pressure is increasing. Okay. If pressure increases, what should happen to the temperature? Temperature should also increase, and that is what we are noticing. From here, the temperature is rising up. And after that, we should again get a constant uh, pressure. This is a constant pressure graph. Okay. So from the constant pressure graph, this time now pressure is decreasing at constant volume. So this is a constant volume. As pressure decreases, temperature decreases. So now tell me, in this case, which is point A, B, C, D now? So you would see here, this has to be point A, this has to be point B, this has to be point C, and this has to be point D. Then only it will justify. See, A to B, it is uh, uh, baric expansion. Okay. 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 Next, B to C is an isocoric. This is isocoric process. Then C to D is again isobaric compression, and D to A is isocoric process where we have a constant volume. Got it? So this is the graph. The transformation is clear, everybody? So given any graph, you should know how to transform, right, between pressure versus volume and so on. Okay. Let me take one more graph like this, and this time we'll try to transform. So suppose if the graph is something like this, here, this is the way it is. One graph goes like this, another graph goes like this. Like this. Let's say this is pressure versus volume graph. Okay. I started off with this point, let's say A here, B, C, D. So I'm talking about a cycle A, B, C, D, A. So this is how it is going. This is how it's going. Hmm. So for this case, now let's notice this one. A to B, what kind of a process it is, and this is happening at a constant temperature T1, right? This is happening at temperature T1, this is happening at temperature T2. So this is an isothermal process. So C to B is an isothermal process, or B to C is an isothermal process. D to A is also an isothermal process. Okay. So tell me, what are the processes? Let us name them first. A to B is what? Isocoric. This is isocoric process. And uh, isocoric process here. And then B to C is isothermal. And in that isothermal, have you noticed the volume is decreasing? So it is compression. It has to be compression. And thereafter, C to D. If you notice C to D, what is happening? This is at isobaric process. This is isobaric process. And thereafter, we will have D to A. D to A is isothermal expansion process. Isothermal expansion. And these are the processes. Let us do the same graph transformation once again. So let me just copy this one. So for this, I'm trying to make a graph transformation between T and A. T and V, how does the graph changes? Let's see. Starting from A to B, it has to be isocoric process. So that means I need to have lines like this. Either the line will be here, okay, or the line will be somewhere here. This is about A to B. So we are just predicting whether it is this line or that line. We'll be able to observe based on how the next part is, whether expansion or compression part is. See, the next part is what? We have isothermal process, right? If it is isothermal, it has to be constant temperature. It should be like this, isn't it? But here there should be a compression. Here there should be a compression happening. That means volume should decrease. So suppose originally, if at all I take A to B, pressure is increasing. Pressure is increasing at constant volume means temperature should increase. So that means definitely the graph originally should be going like this. Okay, upwards like this. And thereafter we got constant temperature line. We got constant temperature line, something like this, where compression is happening, so it has to go this way. And thereafter, again you are operating at constant. So now since we got this, I remove this line now. After that, we have to operate at constant pressure. From C to D, I have to make it as a constant pressure valve. So constant pressure means at constant pressure, temperature and volume graph would go uh, crossing through the origin like this. This is the way it will go, isn't it? So passing through the origin, this is how it will go. One second. So somewhere like this it should go. And thereafter again it should go at constant temperature where expansion is happening. So that means this is the line we should look out for, like this. So here this is the way it should come, and thereafter this is the way it should go. Okay, isn't it? Now we got all the points perfectly. So you can see we started off with this point A, we went all the way B here, then we went to C here, then we went to D here, and these are the arrows of that. So I hope all of you understood how the transformation happened from this graph to this graph. Any doubt? Clear? Okay. So let's work on a simple question first. Everyone, work it together now. Find the uh, Q net of system in kilojoules if an ideal gas is subjected to following cyclic process. So it is going from A to B and then towards C. And what are the factors that is given is this one. It is given that this point and this point here, this point and this point here. The values of those are given. So here is given as 40, 20. This is 1 and this is 2. This pressure is given in bar units. This is a volume which is given in liters. Clear? Now, while doing these kind of questions, I never ask you in the question to find out the individual path, work done, or heat. That means We are not interested about how it is going from A to B, then B to C, then C to A. We are directly interested on checking out the overall heat or overall work done. Now I can say one thing, that this is a cyclic process, and cyclic process du will always remain 0. So that means delta u of the cycle ABCA will be equal to 0. So which means Q net of ABCA has to be equal to minus W of ABCA. Yes or no? Okay. That is something which you need to understand. Clear, beta? Right. So now, if that is the case, you know that I just need to calculate the overall work done. Now, overall work done, when you have a pressure and volume graph, it is always area under the curve, right? So first, suppose if at all I go with this one from A to B, let's say A to B. For A to B, what is the area under this curve here? So from here to here, I need to check out how much is the area you will get. So from here to here, this is in first process. Everybody, this is in first process A to B. In A to B, so whatever we get, it is the area under that particular graph here. So this is the area under the graph. Correct. Now tell me, this is an expansion. So is it positive work or a negative work? This will be negative work done. Make sense? So this is work done, which is negative, correct? Next, B to C. B to C, how will be the work done now? So B to C will be like this here. This is how the work done is. And from here it has been starting, right? So like this. B to C, this is how it is coming out. And in that case, work done will be area under this curve. So if you notice area under this curve here, so this is the area under the curve now. So now if you check it out, area under this curve will be like this. This is the area under the curve. And now, this time if you compare the work done, this work done is actually positive. This is positive work done because it is compression. Compression is always a positive work done. Correct? And C to A, if at all I write it from C to A here, correct, like this, obviously work done in this case is 0 because there is no area under this curve we can get because it is at constant volume. So this is C to A and this is B to C. Okay. Now if I join all three of them, correct, if I join all three of them, then I should get the work done, correct? So now let me take this entire graph once again. Clear? Let me show that here at the end. Okay. Now what will be the work done, everybody? So originally, if you notice, this was the work done. Okay. This was the work done by the process A to B. This was work done from A to B. Correct? But that was a negative work done. Everybody, that is negative work done. And then I saw that this is the work done, which is positive work done. Correct? Now tell me what will be the net work done. Can I say the net work done is actually simply the area under this curve, right? So that will be work done net. Clear, no? This is the net work done. So net work done will simply be area under the enclosed figure. Remember guys, everyone. So whenever it is a cyclic process, area under the enclosed graph, that will be the work done. And now tell me whether it is positive or negative here. Please check. Because this is the total work done from A to B. This is from B to C. Which one do you think is larger value here? A to B, right? A to B is much larger value compared to this one. So overall it is negative or positive? Overall it is negative, isn't it? Overall work done is negative. So from here we are getting one important conclusion, that is, if at all your cyclic nature, the cyclic process nature is clockwise in a PV graph, if it is observed clockwise, then the overall work net will always be negative. And if it is anti-clockwise, then overall work net will be positive. Clear, everybody? So now let's figure out that note for clockwise cyclic process, work net is negative. For counterclockwise cyclic process, W net is positive. Okay. So from here I can say the same logic fits for heat also. So for heat, because work is same as heat, only thing that is changing here is sign. That's it. So Q net will be greater than 0. Q net will be less than 0. So in this case, we asked for W net and Q net. So what will be W net now? W net in the given question will be equal to area under the graph here. Correct? So that will be area under the graph. So what is the area under the graph? Half into base. Base is this one, which is A to B. A to B is how much difference here? 20 units. And what is height here? 1 unit. So 20 into 1. So which is how much? Minus 10. Okay. So minus 10. And overall, I told you that it is clockwise. So it has to be minus. So minus 10. What are the units given? Bar and liter. So this is bar liter. And bar and ATM are very similar. Remember, one ATM liter is 101.3 joules and one bar liter is simply 100 joules. So therefore, I need to simply multiply 100 here. 10 into 100. So that makes it 1000 joules. So this much is the work done net. So what will be the Q net? Q net will be equal to 1000 joules with a positive value. So this much amount of heat is given overall to the system in this process. So from A, B, C, as you complete the cyclic process, this much amount of heat was given into the system, and the same amount of heat is been utilized to completely do the work by the system. Clear, everybody? Please go through it once. If you have a doubt, let me know. Samyak, is that clear, beta? Right. Ishman? Right. Sorry. You can just show a thumbs up. That's all. That should be good enough. Utsa?
Yes, sir.
Right. Quickly notice these examples. See, if a graph is given P versus V, right, and there are two cycles given, You always see the complete cycle, you know, individually. So suppose this is one cycle, and then this is one cycle. Now, what are the cycles like? See here, since it is going like this from here to here to here, what is this one? This is a clockwise cycle, isn't it? So this cycle has a clockwise manner, right? What about this cycle? Here you see that B to C, C to some point here, and from there to B. How is it going? It is going anti-clockwise. So that means this part is a positive work done, this part is a negative work done. But as per the figure, which is bigger in size, this one is bigger in size. So therefore, this value, since W2 is greater than W1 by magnitude, overall cyclic structure, overall cyclic, the work done will be positive, net work done will be positive, and net heat will be negative. So here Q net will be negative and W net will be positive. Second case, see, here again from this point, this is the way it is going like this. So this is a negative work done here, and in this cycle, it is positive work done here. So obviously the negative part is much bigger than the positive part. So overall work net has to be negative and Q net has to be positive in this case. Third case, you see this is the way it is going. This is a clockwise cycle. This is a counterclockwise cycle. So this is negative work done and this is positive work done. Correct. So obviously overall work done, the negative work done is more clear. So you can see this is how it is going. This is clockwise and this is counterclockwise. So overall net work done is less than 0 and Q net is greater than 0. Okay. What about this one? If they have equal size, one is clockwise, the other one is anti-clockwise, then W net is also 0 in this case. W net is 0, Q net is 0. And next one, here you can see this is the way it is operated. This is clockwise. Actually, this is the same thing which I have given it already. Now, what I gave you is the pressure versus volume graph earlier. Now, this is volume versus pressure graph. Now, if you take volume versus pressure graph, correct? In volume versus pressure graph, the uh, fundamental is exactly opposite here. So, here clockwise, here if you see clockwise cycle will make work positive and counterclock cycle work net will be negative if for V versus P graph. Okay, that's the difference. So this is V versus P graph. So this appears to be clockwise and this appears to be anti-clockwise. So, since this is clockwise, it is positive. Anti-clockwise, this is negative, right? So overall, positive value is dominant. So that's why work net will be greater than 0. Q net will be less than 0. Done. I suppose all of you understood this part. Now let's do, a little difficult question. Actually, this was a very standard question asked in Olympiad. Every year in Olympiad, either in first level or second level, the type of question which we are discussing is asked. Okay. In fact, this has started trend in JEE Advance also. In physics, as well as in physics also, very similar type of idea is used. So if you understand the idea, it becomes easier to figure out how to get that. Okay. So let's try this question now. Suppose if at all I have 1 mole, right, of an ideal gas, 1 mole of an ideal gas is carried through a cyclic process a reversible cyclic process as given in the figure. Find okay find the maximum temperature attained maximum temperature attained by the gas during the cyclic process in terms of R. So we have to write the answer in terms of R. Okay. The graph was given this way. Okay. So this is A, B, and C. Correct. So it is going A to B, B to C. Sorry, B and C are reversed. B is here, C is here, and C to A. This is how it is going. Pressure versus volume it is given. Okay. Now let's see what are the challenges that we face here. Okay. First, the data is given here. Let me write the data also. The data given here, 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 and here at these 4 points. The data given is 1 liter. This is 2 liters. And here it is 1 bar pressure. And here it is 4 bar pressure. This is 4 bar pressure. Okay. Now, notice one thing. A to B is a defined process. And what is that process? It is an isochoric process. C to A is also a defined process, which is isobaric process. But what about B to C? Can you see B to C is some polytropic process, isn't it? Simple processes which we figured out, that is isothermal, adiabatic, isobaric, isochoric. It is not falling into any of that kind, right? It is a process where B to C, that is pressure versus volume, are linearly dependent on each other. Is that clear? So it is some kind of a polytropic process where it is linearly dependent on each other. Now, if you recall something from, Boyle's law when we discussed, right? So pressure versus volume, we used to write the graphs like this continuously, isn't it? And if this is operated at temperature T1, T2, T3, T4, T5, one thing we are sure of that T5 is greater than T4, greater than T3, greater than, and so on. Isn't it? Yes or no, everyone? That means as you go away from the pressure and volume, away from the origin towards the graph which is outward, then it is operated at a higher temperature. Okay. It also makes sense because PV is equal to nRT, and this PV is the one which is constant, right? And this constant only depends on temperature. And if temperature has to increase, the product value of PV should increase. Tell me, when will the product value PV increases? When the pressure, it's not like pressure is high, volume is less. Then it is not, a good deal. Or neither it is volume is high, pressure is less. Then also the product of P into V has to be optimum. That means it has to keep only increasing. That only happens when you go away from it. So that means somewhere the point here, 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 like this, isn't it? So your temperature would be higher and higher as you move away from the nucleus. So now tell me, as you move away from this origin, now where is that maximum temperature we can attain? Not anything on this line, not anything on this line, definitely away from the center. So away from the center is this line, and on this line somewhere you will find there is a maximum temperature. Got it? And probably the graph would go like this, somewhere like this it will be going like this. So somewhere here you will have a maximum temperature value. Got it? So we are supposed to find out where is that maximum temperature value. So one thing we learned, that the maximum temperature will lie on B and C. Is this point clear? Now, learning that maximum temperature will be present on B and C, now I need to create, first we need to generate an equation for B and C. So B and C is a equation of a straight line. Now, we know the dimensions of these 2 points. At this point, the dimension is x is 1, y is 4. At this point, the coordinates are, 2 and 1. Correct? These are the coordinates. Right? So what is the equation from B to C here? I can write equation of a line. Equation of a line will be equal to y minus y1. Y minus y1 is equal to m into x minus x1. Correct? M being the slope. So slope value will be equal to how much? Y2 minus y1 by x2 minus x1. And how much is y2 minus y1 here? Y2 is this one, 4. Y1 is this one. This is y2 minus y1. So 4 minus 1. So 4 minus 1 by x2 minus 1. So that makes it one second. Yeah. Clear, everybody? Right. So how much we are getting here now? Y2 minus y1. This is the value we have, and x2 minus x1. Hmm. So how much are we getting here? So we are getting this as 2. Clear? Now tell me, in this case, once we got these values, if at all I put this as, what is y? Y is actually a pressure term. So P minus P1. Let us write this P1 as 4. That is equal to 2 times of V minus 1. Okay. So what are we getting? V is equal to minus 4, sorry, plus 4 plus 2V minus 2. Right? So P is equal to 2 plus 2V. Okay. I think I'm getting something wrong. One second. What did I
So
got it
the
from?
slope should be 3, right?
Sorry. Slope should be 3. Hmm.
Sir, I think the slope should be -3 because it is decreasing.
Sorry. So it's minus 3, correct? Hmm. So it should be minus 3. So we get this as 4, P minus 4 is equal to minus 3V, and this should be plus 3. So how much are we getting? So P is equal to 3V plus 7. Did you get this? Everybody check. Now, pressure and volume term are related with each other. As per the equation, we got this, how they are related with each other. Hmm. So P is equal to, sorry, minus, P is equal to 7 minus 3V, correct? So this is simply 7 minus 3V. Okay. Now tell me, if this is the pressure, if at all I put it in something like PV, correct? And we want to get a maximum temperature. So that means you differentiate that in terms of T. What should we get? We should get volume term, isn't it? At that maximum temperature, what is the volume term we should be able to get? And if you know the volume at that particular value, we should be able to figure out what is the temperature. Correct? So that's what we can do now. So we know that P into V, clear, is equal to nRT. So pressure is 7 minus 3V into volume is V, that is equal to nRT, correct? Clear everybody? Okay. So I know that at T max, d of PV by dt has to be equal to 0. Okay. Because at this point, if at all you differentiate that, sorry, with respect to V, this has to be 0. Either you can differentiate that with respect to P or with respect to V. That function has to be 0, correct? So what can I do that? In that case, I can say 7V minus 3V square. This is a function which we have, PV. And if at all I differentiate that with respect to V, so what am I getting here? So I'll get this as V minus 3V, that is equal to 0, correct? 6V. 6V, that is equal to 0. So V should be equal to 7 by 6 liters. Does that make sense? Clear everyone? And now at this particular volume, put that value here. So what do I get? So 7 minus 3 times of 7 by 6 into V. V is 7 by 6. That is equal to 1 mole into R into T max. So this is the T max which I need to get. Okay. So this goes 2 times. So 14 minus 7 by 2 into 7 by 6, you know, divided by R. So T maximum will be equal to uh, this is 7. So 49 divided by 12. 49 divided by 12 R. So this is the maximum temperature at this is the temperature where you can I mean this is the temperature which is maxima in this cyclic process. All right, please check this out. Everyone, please go through it once and let me know. Finished? Everyone, please check. Free expansion. The next process itself is called as free expansion. Okay. See, when we say free expansion, so which means you are keeping an environment such a way there is a gas inside this chamber, which is our system, and externally here there is only vacuum. So which means the P external is zero. If P external is zero, if there is no external force, work will be zero because that is supposed to be minus P external into dV. And tell me, if there is vacuum outside, even if you want to exchange the heat from surroundings, there is nothing to, I mean, there is nothing which can actually absorb or uh, transfer heat. So therefore, heat cannot be exchanged either. You can see heat cannot be exchanged. Work cannot be done. So if Q is 0, W is 0, which means delta U should be 0. And if delta U is 0, consider for an ideal gas. If it is for an ideal gas and delta U is equal to 0, then NCV delta T should be 0, which means NCV delta T should be 0, which means delta T should be 0. If delta T is 0, delta H will also be 0. Okay. Now this is subject to only ideal gas, remember. Okay, this is general. Whether it is ideal or anything, as long as we have vacuum outside, this is always valid. But when delta U equal to 0, delta T being 0, delta H being 0, this is only for ideal gas. Next. Since it is an expansion happening at a constant temperature, I can say this is isothermal process. But since it is happening on its own, I can say that it is an isothermal irreversible process. Isothermal irreversible expansion. Correct. As per what we are saying, it has to be isothermal irreversible expansion. But at the same time, I'm also noticing that Q is equal to 0 makes it as adiabatic. It also becomes an adiabatic irreversible expansion. So have you noticed free expansion is itself a mixture of two processes, which is isothermal irreversible expansion as well as adiabatic irreversible expansion. Okay. Only thing that is being non-zero is volume, change in volume, which is increasing because gas is only going to get expanded and pressure of the gas is decreasing. So you can see this process is both adiabatic and isothermal in terms of expansion. Everyone clear? Any doubt here? So this is an irreversible form and that's what you will notice. Now, let me write one more question here before I wind up. Okay. Usually, first law questions, sometimes it will be given to calculate the work done in a chemical reaction. But here, do not worry about what happens to the delta H, delta U and everything. We can simply do that in an easier way. See, work done in a chemical reaction, chemical reaction. These are very simple cases. These are those cases where uh, originally the species present in the system are either solids or liquids. For example, I have zinc and then I am adding HCl. Okay. And you know that zinc in HCl will dissolve easily to convert into ZnCl2 and releases H2 gas. So what happened? Originally, imagine like this, you have a test tube wherein you have small amount of zinc being added here and then you have added HCl, correct? Now, as soon as you add it, within no time, now imagine you have closed this. Okay. So initially when you started, the system was only up to this point. This is the system. But now, as soon as as soon as the reaction takes place, what happens from here? You will see the entire test tube will start covering up by hydrogen gas. So I can say originally, if this was the volume V1, now due to the entire volume got increased here, sorry, this value here, from here to here, this will be V2, isn't it? So I can say that the total volume change is observed. So in the system, there is a total volume change. So delta V will be equal to V2 minus V1, correct? And since V1 is very small, very small, delta V can be almost given equal to V2. That is the total volume occupied by the gas. Volume occupied by the gas. So this is nothing but volume occupied by the gas. So which is nothing but volume of H2 gas in this case. Okay. So if that is the volume of the gas occupied, how do I write work done? Work done is equal to minus pressure, given by that H2 gas into delta V, and delta V can be simply written as volume of H2 gas directly. We can ignore the fact that what is the volume occupied by zinc or zinc chloride and all, because they are very, very small value. And now it is the pressure of H2 and volume of H2. Can I simply write it? Can I write this as minus n number of moles of H2 into R into temperature. So this is how you can calculate the work done, which is equal to number of moles of H2 into RT. So sometimes simply this information is being given. That is, what are the number of moles of hydrogen gas or any gas that is generated, and what is at what temperature it is happening. So if you just know that, you can easily calculate. Okay. Clear, everybody? Right. This is the other variety that could be asked. Okay. So as much as first law is concerned, correct? This is how much you need to know. Okay. Thereafter, everything what you need to know is about uh, thermochemistry part. Once you know the thermochemistry part, it becomes even easier to apply more examples. You'll be able to deal with much more examples once you get an idea about this. Okay. Now, last thing, before starting with thermochemistry, there is one last factor which I'll explain that. Then after, we can start thermochemistry in the next class. See, let me put it here itself. Yeah. Isotherm versus adiabat. Isotherm versus adiabat. What does that mean? See, suppose if we draw the graph for P and V, you know that for P and V, this is how the graph would vary. Okay. Right. This is the pressure versus volume graph. Right. But you know that when it comes to pressure versus volume graph for an isothermal process, let's say this is how the isothermal process is. Okay. Now, an isothermal process, pretty much you will see the graph goes like this. This is the graph that will go. So this is for isothermal process. Now for an isothermal process at any point of place, let's say this is the point of place where I'm talking about, and any point of place here, if at all you're trying to find the slope of this point, slope of the curve at this point, that is what we call it as isotherm. That is called as isotherm. And how do we represent as dp by dv, isn't it? So suppose if we have PV equal to constant, then if at all I differentiate that, what do I get? If at all I differentiate this, what do I get? So I'll get this as V dP plus P dV equal to 0. So that is V dP by dV plus P equal to 0, or dP by dV, which is the slope, is equal to minus P by V. Let me put this as equation 1. Okay, clear? And let me take out a similar graph again, okay, which I'll put it on this side. But this time I'm trying to find out the graph, but what you would notice is the graph goes little like this, and rest of the point, the slow point will be like this. Now, the graph which I'm talking about is this is for an adiabatic process. And the point where we are finding out, this is the slope of curve at this point. Curve at this point is called as adiabat, which is also represented by dp by dv. Now, if at all I do dp by dv here, what would I get? See, I'll do it with the other color. So we know that PV raised to power of gamma is equal to constant for an adiabatic process. So I can say this as V power gamma into dp plus uh, P times of gamma into V raised to power of gamma minus 1 into dV is equal to 0. This is what we, if at all I differentiate that with respect to V, this is what I'll get. And now V raised to power of gamma into dP, V raised to power of gamma into dP plus P gamma into V raised to power of gamma divided by V into dV equal to 0. Now you can see V raised to power of gamma is coming out to be common. So if I remove that, I'll get dP plus P gamma by V into dV equal to 0, or simply dP by dV is equal to minus P gamma by V. And you know that gamma is always greater than 1, right? So which implies here this is an slope of an adiabat. This is the slope of an isotherm. Which value looks to be more negative here? So you can clearly make out that this is more negative. So therefore, dP by dV of adiabatic is more negative, than dP by dV of isotherm. Okay, isothermal process. Okay, therefore, if at all we plot the graph for both isothermal and adiabat, if this is how isothermal graph goes from a starting point here, then adiabatic graph will always go down here like this. So this will be the adiabatic graph. Okay. So at any particular point of volume, if at all you, let's say this is the point from one point here and this point, at these 2 points, if you calculate, for adiabatic, you'll always have more negative slope. Okay. So I suppose all of you understood that. And if you recall, we learned that if adiabatic process is being operated irreversibly, the point will come above it, right? So which means adiabatic irreversible expansion will be always between these 2 points, correct? So somewhere in these 2 points, you will have, you know, adiabatic, irreversible expansion. Okay, will always lie somewhere between these 2 points. So this is the graph between P and V. Clear? So from here, during expansion, let's say this is point A, this is point B, point C, and point D. Okay. During expansion, during expansion from point A to B, A to C, or A to D. Okay. What happens to the temperature? Temperature here remains T1, correct? Because here temperature will remain T1 at the A end also, at the B end also. But here it changes. Here it is T1, here it will become T2. Here it is T1, here it will become T3, right? So temperature at A will be same as temperature at B. But temperature at A will be greater than temperature at C. Temperature at A will be greater than temperature at D, correct? Because it is an expansion, the temperature has to decrease for sure. But what you will notice therefore is that temperature of B will be greater than temperature at C will be greater than temperature at D. And you know that B point is an isothermal expansion. C point is an adiabatic irreversible expansion, and D point is an adiabatic reversible expansion. Okay, so this is an important conclusion that to be drawn. So this can be explained based on understanding what is isotherm and what is adiabat. Okay, so I hope this point is clear, everybody. Right. So I think we'll stop the session here now.